we still have to cover a few things from yesterday's talk. We are on 14 out of 18, and what we had discussed was the conflict between quantum theory and general relativity. I tried to explain how gravitation and quantum theory both are emergent phenomena. Okay. So, now we want to start talking of the parallels between the gauge theories of particle physics, especially we will focus at electrodynamics, which is used to construct the quantum theory of electrodynamics QED. And we will see in today's lecture what are the similarities between electromagnetism and gravitation and what are the differences. So, this you are familiar with. Electromagnetic vector potential and field tensor are a way of writing Maxwell's equations. These field equations are invariant under gauge transformations, and those gauge transformations form this group U1, the so called Lie group U1. Let us try to understand what that means. U1 is a group of complex numbers of unit magnitude e to the I theta. So, magnitude is 1, and these cause what are called unitary transformations of the wave function of a particle, say a electron. So, consider a complex scalar field psi. It can be a spinor field also, but for simplicity let us consider a complex scalar field psi with the following local U1 symmetry. What does that mean? U1 element of the group U1 is e to the I theta. So, I want to multiply psi of x by e to the I theta of x. So, if theta depends on x, it is a local symmetry. If theta does not depend on x, it is a global symmetry. We do not want any change in the field equations if we make this phase transformation on the state. So, this is called a gauge transformation. Now, under this transformation, what happens to a derivative like del mu of psi? Yeah, you see what I am saying? Psi changes like this, but how does del mu of psi change under this gauge transformation? So, apply this del mu function on e to the I theta psi. What will happen? You will get e to the I theta del mu psi, that is this term, but there is one more term, I del mu theta e to the I theta, this one. This is not good. You see, you want everything to transform just under a gauge transformation. The derivative should also transform like this. I want only the first term. But I am getting this extra, and that is not good. We do not want that. So, hence we introduce the gauge field, the electromagnetic vector potential into the theory, which we assume under this transformation e to the I theta on the state, the vector potential is assumed to transform like this. If you introduce this phase function theta of x, psi of x transforms like this, a mu, the vector potential, is assumed to transform like this, where E is the charge of the electron. So, this is a gauge transformation of the electromagnetic vector potential. Now, instead of del mu, define a covariant derivative d mu. So, we are discussing this because something very similar will happen in space time in general relativity. Define this covariant derivative d mu of psi as del mu of psi plus e to the I a mu acting on psi. So, what is going to happen? Under a phase shift, del mu of psi has an extra term which we do not want. That extra term will cancel with how a mu changes under a gauge charge. You can see a mu is having del mu theta, it will cancel this del mu theta, you can check that. If you, what I mean is apply this covariant derivative d mu on e to the I theta. D mu of e to the I theta will give you this. You get what I am saying? Yeah? Under a gauge transformation, d mu of psi transforms just like the state itself, and the field equations will then be invariant, because this e to the I theta will cancel out with its complex conjugate when you write down the field equations. So, this is how we introduce covariant derivative into a theory, because we want under gauge transformations there should be no change in the field equations. The covariant derivative also transforms the same way as the state does. The ordinary derivative does not transform nicely. And what is the analogy with space-time, with general relativity? This object, which is what we call a connection, the Christoffel symbols will come here. They ensure that the derivative transforms in such a way that you can compare vectors at 2 points in space. This is the kind of change that comes because we will see that soon, because of parallel transport. If you parallel transport a vector from one point to another, then because the coordinates are curvilinear, you will pick a term like this, which we do not like, and that will be cancelled by redefining the covariant derivative. If you have the Lagrangian, then demanding gauge invariance of the Lagrangian under these transformations ensures conservation of electric charge. So, I have not proved that, we will leave this for the future, but I think you get the idea that in electrodynamics also there is a concept of a covariant derivative, and the role of the connection is played here by the electromagnetic potential. In general relativity, the role of the potential will be played by the gammas, the Christoffel symbols, or we call the Levi-Civita connection. They are forces. So, this is one very interesting difference between electrodynamics and general relativity. Here the connection is the potential. The corresponding potential in general relativity is the metric. That is not the connect. The metric does not play the role of the connection. The derivative of the metric, the Christoffel symbols, play the role of the connection. So, there is a connection, a covariant derivative in both the theories, but the role of the connection is being played here by the potential, there by the forces. So, that is something deep. Maybe we will discuss that as we go along. So, any questions? Okay. Now, moving slowly and connecting with the topic of today's second lecture, we will start shortly. The language of differential geometry. So, some of these things will be proved subsequently. The language of differential geometry brings electrodynamics even closer to general relativity. My space-time is what is called a differentiable manifold. We will define a Levi-Civita connection on it. So, please take these just as definitions for the future. We will define a connection one form and the curvature two form when we start differential forms. Connection one form has the same information as the Christoffel symbols, but written in a more geometric way. The curvature two form has the same information as the Riemann curvature tensor. Gravitation as a Riemannian geometry then requires the introduction of the metric as a potential. On a differentiable manifold, we need not have we do not have a metric. We have to add additional structure. Okay? When you add the metric, you get what you call a Riemannian geometry. Electrodynamics is not a Riemannian geometry. It is at this level, you have a connection, you have a curvature. The field tensor in electrodynamics is the curvature. The electromagnetic vector potential is the connection. The field tensor is the curvature. Analogous to the U1 gauge invariance of electrodynamics, in space-time geometry of general relativity, we have diffeomorphism invariance. What does that mean? invariance of the theory under coordinate transformations. You make coordinate transformations at every point in space-time. Your field equations should have the same tensorial interpretation. The group of all coordinate transformations together is what we call diff-M. Gauge theories are also geometric theories on a fiber bundle. This is what I like to explain today. A fiber bundle is a base manifold plus a fiber space. Base manifold is space-time. On space-time, you add another manifold, which is a set of fibers. For example, so yeah, my teacher used to give me this very basic example. Jhadu. A jhadu is a fiber bundle. You know, you keep a broom or a jhadu on the ground like this and make it stand up. Each strand of the jhadu is a fiber. The base space on which sitting is space-time. What is the role of the fiber? The coordinate transformations which relate to gravity are taking place on the space-time. The gauge transformations of the electromagnetic field are taking place on the fiber, because both spaces are having gauge transformations, but they are in different spaces. For gravity, it is in space-time. For electromagnetism, it is in the fiber space. That you roughly get the idea. So today we'll talk more about that. The electromagnetic vector potential is a connection 1 form that I said, and the field tensor is the curvature 2 form. The gauge transformations in fiber space have the structure group U1. So the transformations belong, I'll define structure group today. The difference between gauge theories and Riemannian geometry is the metric. I keep saying this again and again. Where does the metric come from? This is a very deep question. They both have this structure of a connection and a curvature, both electrodynamics and general relativity. But general relativity has something more. It has a metric, which is what makes it different from gauge theories. And I will try to get a little deeper into this question as we go along. What is the origin? So if there is unification of the forces, there probably is no metric. Somehow the symmetry breaking that separates the forces give rise to a metric. Any questions?
Maybe this diffeomorphism and the coordinate transformation, are they
The same thing.
strictly same?
Yes, yes. The set of coordinate transformations are what we call diffeomorphism. Okay. Generalized coordinate transformation is generalized Lorentz. Lorentz transformations are from one flat space-time to another, but you make the same transformation everywhere. No? Space-time is globally flat. One Lorentz transformation will rotate the frame. But generalized Lorentz coordinate transformation is different transformations at different places. Del x prime I by del x j is a coordinate transformation. It is a function. This function will change from place to place. That's generalized. But if this is a Lorentz transformation, this will not be space dependent on the point where you make the transformation.
This is equivalent to general principle of general covariance.
Yes, the principle of general covariance says that under general coordinate transformations, your equations should retain their tensorial form. So we don't call it invariance, we call it covariance. It is transformed like tensors do. So we'll be talking of coordinate transform. Yeah. Diffeomorphism, invariance, and general covariance, I think, are the same thing. Yeah, that's what you are asking. Yes. They to me, they mean the same thing. Yeah. Yeah. I would say, I don't see the difference between that and diffeomorphism invariance. Yeah, it's the same thing. It's just that here we're talking the language of a group. The group of general coordinate transformations which leaves the theory generally covariant, that group is called diff-M. Okay? Yeah, please.
The way you gave an instance of the fiber bundle
Yeah.
by giving that example.
Yeah, yeah.
So if we consider a space-time manifold,
Yes.
and can we consider a bundle of hypersurface orthogonal geodesics as fiber bundle?
Okay, let me try to understand your question. On a space-time manifold also there is a manifold fiber bundle associated with the space-time. What is that? At every point in space-time you have a tangent space, because like you draw the tangent vectors at a point, they lie in a tangent space. That tangent space is a fiber. The set of fibers at the set of tangent spaces at all points is the fiber bundle of tangent spaces. It's close to what you are saying. So instead of saying geodesics, I would say the tangent space. That's also a fiber. Very good question. The tangent space is the fiber of space-time, and this U1 group will give me the fiber bundle of electrodynamics. Both are fiber bundles, but they are of two different kinds. So this one is a vector space. In space-time, it's a vector space. In electrodynamics, it's not a vector space. It is what we call a Lie group. A Lie group is also a manifold. The U1 is a Lie group, which is made from a set of complex numbers e to the I theta. So that is a what did I say? That's a Lie group. If the fiber is a Lie group, the fiber bundle is called a principal bundle. If the fiber is a vector space, we call it a vector bundle. You get what I am saying? Both are fiber bundles, but of a different kind.
Right. So in general relativity, that becomes a vector space, and in electrodynamics, that becomes a Lie group.
Yes. So that's a profound difference. And so we want to get to the heart of the matter, that in unification, what will happen? I have to separate a Lie group from a vector space. When I unify, I have to think what am I supposed to do. And the tangent space is having a metric. The Lie group is not having a metric. So what is going on here? There must be something. They are similar, but they are not the same. When you see a situation like this, you should get suspicious. You want to exploit the similarity. That when I unify, what do I get such that after symmetry breaking, this separate structure? You get what I am saying? So like some work the people try, we are also trying to convert somehow from the tangent space of space-time to a Lie group. In this case SU2. So I think I'll talk a little bit about that. So that the fiber bundle of general relativity starts looking like the fiber bundle of electrodynamics. But there also there will be a subtle thing which will bring in the metric. I can convert this vector space into a Lie group, but I still need the metric. And what we were trying to do is get rid of the metric so that the whole thing looks like a gauge theory. So it's not a solved problem, but worth discussing. Okay? All right. So good. We are making decent progress today. So I have given you some idea of the similarity and differences between electrodynamics and general relativity in the language of differential geometry. And so now this is just a sort of glimpse from yesterday's lecture, that we should be aware that there are many different but equivalent formulations of general relativity, and one should try to learn as many of them as possible, because they bring new insights. So first one is the standard thing which we do in any coursework, the metric based formulation with a metric compatible connection, the Christoffel symbols, which we call the Levi-Civita connection. This is what also comes from the Einstein-Hilbert action, integral r root minus g d for x. The tetrad, or equivalently the vierbein formulation. Vierbein is a German word which means I think 4 legs, 4-legged. So a let's get used to tetrads. A tetrad is a set of 4 vectors. Each is a vector in space time, and there are 4 of them, yeah, and they are denoted by this symbol E. So this upper index A, okay, these are Roman letters. The A index tells which vector. E1 is the first vector, E2 is the second vector, E3 is the third vector, and E4 is the fourth vector. Each vector has 4 space-time components. Those are labeled by mu. You get the difference? A labels, upper Roman A labels which vector. The lower Greek label tells the components of that vector. This is what we mean by a tetrad, and the definition is the following. A tetrad helps you set up a local Lorentz frame. At every point in space time, you can set up, because of principle of equivalence, if you free fall, you will be in a Lorentz frame locally. On that Lorentz frame, you want 4 vectors, 1 time-like, 3 space-like, so that you can set up a coordinate system locally. That is called a tetrad, and it is defined by this condition. The metric is basically bilinear in the tetrad. Multiply 2 tetrads together, contract it with the local Minkowski metric, you should get. So this is the definition of a tetrad, and a vierbein refers to the fact that there are 4 tetrads. So this is the formulation of general relativity in terms of tetrads and what is known as a spin connection. Spin connection essentially the same thing as the Levi-Civita connection with some qualifications, but it may look so what is AB? These are different spin connections. There will be, if in 4-dimensional space time, there will be 16 of them. A takes 4 values, B takes 4 values, and mu is its space time index. Okay, so we will come to this, don't worry. Then the Palatini formulation uses the metric and connection as independent variables in the action. Unlike here where metric is varied, here metric and connection both are varied. The ADM formulation, which you are probably familiar with, is based on making hypersurfaces on space-time, space-like hypersurfaces, on which the 3 metric is defined, and then the so-called lapse and shift function. The 4 metric is decomposed into a 3 metric, a lapse function, and a shift function, and the dynamical quantity is the 3 metric. The Ashtekar formulation, this is a formal definition, a SU2 connection and a triad instead of a tetrad. Cartan formulation we will talk about as we go along. This is very interesting, that there is something known as torsion, which you may have definitely heard of, which is the antisymmetric part of the connection. We take the gammas, the Christoffel symbols, to be symmetric, but in principle the connection can have an antisymmetric part, gamma AB minus gamma BA. The antisymmetric part of the connection is actually a tensor, and that is called the torsion. So torsion is, let's say, the other half of curvature. General relativity has, you say, 0 torsion and non-zero curvature, but in this teleparallel formulation of general relativity, it's called TEGR, teleparallel equivalent general relativity. You have a flat connection, the Riemann curvature tensor is 0, but the torsion is non-zero. So this is very interesting. You can formulate general relativity using torsion instead of curvature, or curvature instead of torsion. Both are equivalent. Okay, the Plebanski formulation writes general relativity as these are just terms right now. We will see a little bit more about this, I think, as we go along. So, let us just leave this as it is. Okay. So, now almost getting done. Why I thought I should mention this is because those of you, if you are interested in unification, this is probably something extremely interesting. You are probably familiar with the Dirac operator, you have come across that. Or let me make it give you a simple intuitive introduction. These are gamma matrices, but consider the following gradient operator. Let's define a quaternion. I think I should let's first go to the first slide. Let's do this first. There are number systems known as division algebras, which have the following property. Normed division algebra. Normed means you can define its absolute magnitude. What is the division algebra? If take two elements in the algebra A, B, if their product is 0, then at least one of them is 0. That sounds very intuitive. No? You multiply x and y, if it is 0, then at least one of them should be 0. But there are number systems where you multiply two non-zero things and you will get 0. Those are not division algebra, because then division is not defined. So, a division algebra has the standard rules of numbers are there: addition, subtraction, multiplication, but division may or may not be possible, because you don't, if you are dividing by AB, you want AB to be non-zero, but so if you divide by A, it's okay, if you divide by B, it's okay, but if you divide by AB, it's not okay, because AB is this. Don't want that. It's very interesting theorem in number theory, that there are only 4 kinds of division algebras allowed in nature. 2 we are very familiar with: real numbers, complex numbers, then quaternions and octonions. Every time we go down, the dimension doubles. Real numbers 1 dimensional, complex number are 2 dimensional, quaternions are 4 dimensional. First discovered by Hamilton, as you know, 1800 something, because he was trying to explain rotations in 3 dimensions using numbers. So, rotations in 2 dimensions can be possible with complex numbers, but if you want to rotate a vector in 3 dimensions, how do you relate it to a number system? Turns out that that is not a 3-dimensional number system, it is a 4-dimensional number system. Very interesting. This is the definition. There are 3 imaginary units. I square is so a complex number 1 imaginary unit. Here 3 imaginary units, each squares to -1. And the product rule we are familiar with from vectors. Vectors are essentially quaternions. I times j is k, j times k is I, and k times I is j. That is how we do in vectors also. Yeah? So, this is the definition of a quaternion. And then there is only one more division algebra that has 7 imaginary directions, 1 real direction. So, it is doubling of dimension: 1, 2, 4, 8. Okay? And each of the e's here squares to -1, and there is a product rule which I have not shown. It's not as simple to write. It's very clean. There's something known as the Fano plane. If you look up the Fano plane, that tells you how to multiply. The E1, E2 will be E4, E2. So there is a rule. Okay. So now you can ask, what happens if I double it? This is 8, go to 16. 1 real direction, 15 imaginary directions. That's called a sedenion. You can keep doubling, you'll get now. But a sedenion is not a division algebra. If you take a sedenion A and a sedenion B, which are non-zero, the product can be 0. Yeah? So, you get what I am saying. The doubling goes on. There are infinite series of doubling where you get these higher and higher, what are called hyper complex numbers. But division algebras, there are only 4. Now, something very interesting is going on in recent research. Real numbers we use all the time in physics, complex numbers we use in quantum mechanics. Quaternions are essentially vectors. It's a different language for working with vectors or with working with the 4-dimensional space-time vectors in special relativity. So, although we are not very familiar with quaternions, we are always using them without like Maxwell first wrote Maxwell's equations using quaternions. The language in which we write them today is very different. So, there was a mathematician school which favored quaternions, another school which favored vectors. The vectors won, so everybody forgot about quaternions, but they are equivalent. Okay, so we use octonions is something which we have not used. Question? Octonions have become popular in the last few years. So, we are trying to look into this. We had discussed the fiber space of electrodynamics, and if you add now gauge theories like electroweak and strong, everything is, they are all in the fiber space, which is a principal bundle, because the associated groups are Lie groups. It seems that octonions may provide the number system language to unify space-time and the fiber space of gauge theories. So, half of an octonion is like a quaternion. You see, one real and 3 imaginary directions, that is a quaternion. Because quaternions are subsets of octonions. And this part we try to use to make space-time. This part we try to make the fiber space of the particle physics gauge theories. And so, it seems that properties of elementary particles, quarks and leptons, seem to have something deeply to do with octonions. This is ongoing research. The number 8 appears often in particle physics, you do not realize it. If you count quarks of and leptons of one generation, 1 neutrino, 1 electron. Down quarks come in 3 colors, you are familiar, no? Down quarks and up quarks, what's it? Red, green, blue. 3 down quarks, 3 up quarks, 1 electron, 1 neutrino, that's 8. That 8, I am not joking, seems to have something deeply to do with this 8. Then there are 3 generations of quarks, and like second family, third family, like electron, muon and tau lepton, same for every other particle. That number 3 also seems to have some deep connection with the octonion. So, I thought since this is very interesting ongoing research, I will mention it to you. If you just Google octonions in particle physics, you will find a lot of it. So, this is close to my interest. So, when we yesterday were talking here that we want to replace in quantum theory each point by an operator, that or by a non-commuting number, this is where are we? Yeah. Yeah, this is what we have in mind, that we are trying to replace every space-time point by a quaternion, and if you replace it every space-time point and the fiber space by an octonion, we might have a possibility of unifying standard model gauge forces with gravity. So, I thought I'll mention it to you. So, if you have some idea now of a quaternion, I can come back here. Take the 3 imaginary directions of a quaternion, I hat, j hat, k hat, and on space make this kind of a gradient operator. This is a gradient operator. Now, just square it, d3 square, each ij square, k square will give you -1, that will be the Laplacian. The cross terms will cancel, because ij, if you multiply d3 with d3, ij will give you k, but ji will give you minus k, they will cancel. So, the square of the quaternionic gradient operator is minus the Laplacian. This is exactly what happens in the Dirac operator. If you square the Dirac operator, you get the D'Lambertian. I hope if some of you are familiar with that. The Klein-Gordon operator is nothing but the square of the Dirac operator. So, that is why, but here you have to put something known as gamma matrices. Instead, if you are using quaternions, you do not have to put any gamma matrix. There is a square. This is true in 3D, it is little more subtle in 4D. So, the Dirac operator seems to be very profound in general relativity for the following reason, something known as the spectral action principle. This you are familiar with, the Einstein-Hilbert action R root minus g. On this space time, let us write down the Dirac equation, that is this Dirac operator d psi equals m psi. Look at the eigenvalues of the Dirac equation on that space time. You have given a metric, you have curved space time, write down the Dirac equation, find out its eigenvalues, sum the square of all those eigenvalues. That is what is this trace d square. LP Planck length is put to make dimensions correctly. The sum of the square of the eigenvalues of the Dirac operator is proportional to the Einstein-Hilbert action. This is a famous result due to Chamshadin and Cohn known as the spectral action principle. You are able to work instead of the metric, you can work with eigenvalues of the Dirac operator instead of the metric. So, this is related to our discussion. There seems to be something more fundamental than the metric, and those are the eigenvalues of the Dirac operator. You would construct the metric from the Dirac eigenvalues. These same eigenvalues also describes the standard model gauge theories. They also describe fermions. So, I thought I will mention it to you because this is again ongoing research, that if you are looking for a unifying mathematical description of the metric and of the gauge fields and of the Dirac field that describes electrons, the eigenvalues of the Dirac operator on the space-time, after you have added gauge fields and fermion, those eigenvalues are a common thread between all these different fields. So where does that leave us? What we try to do, replace every space-time point by an octonion. On this space, construct the Dirac operator like this, like the way I did it. Instead of 3, you have 7 of them, and work with its eigenvalues, write a action principle using the Dirac operator and its eigenvalues. That may be the unifying action principle from which, after symmetry breaking, space-time emerges and gauge fields emerge and gravity. This is ongoing research, this is not a solved problem. So, you want to ask me something here? I hope I didn't confuse you all too. Are you okay? You have some background with.
I try to learn about the fiber bundles.
Okay, okay. Yeah, please. Thoda loudly, beta. Which FT gravity? What is the FT? Not F of R gravity. FT. What's the full form? BF gravity I know, but FT I don't know. Okay. See, there what you are doing, you are modifying the Lagrangian. Here my Lagrangian is proportional to curvature. In f of r theories, the Lagrangian is some function of curvature, r square or r square plus r. So, I think what you are saying, FT gravity is a special case of the choice of Lagrangians instead of r curvature scalar. I am right now only talking of general relativity and its unification with gauge theories. Maybe one day we have to go to FT, but no, that's not what we are talking. Okay, so I want to end yesterday's lecture by listing my favorite list of some unsolved problems related to gravitational physics, just to give you a glimpse that general relativity is not the end point of our understanding of gravitation. That is my view, that we have gone a long way, but like I showed you yesterday, the conflict between quantum theory and general relativity, until we resolve that conflict, we cannot say that we have understood gravity. There is a deeper theory from which gravity and quantum theory both emerge as approximations. It is that theory we are after. Then we can say we have a theory of everything once we unify it with all the forces. So, string theory was supposed to be that. I say it is not. It has, to my understanding, it has not worked. And the reason why I think it has not worked, that is my claim, is because this is not respected. That in quantum theory, in pure quantum theory where everything is made quantum, there is no classical space-time, irrespective of the energy scale. This is a problem, and I talk to string theorists, we have a disagreement. So I say, you didn't do this, you should have removed space-time from quantum theory before. What they do, they take strings. Every particle becomes an extended object like a string. For each string, you write relations like this that you quantize. But to begin with, they retain a background space-time. They know it has to be removed. They know that. In true string theory, there is no classical space-time. But they have not found that case, how to remove space-time from string theory. So, my contention is that that's the reason why they are stuck. Part of string theory is very beautiful. Every fundamental object is not a particle, not a point particle, it's an extended object. With that, we agree. So, we also say the same thing here. It's an extended object because the space-time itself is like a non-commuting operator. So, it's an extended object, but that is, after that, string theory gets stuck. All different particles and gauge fields and gravity are different excitations of the string. That is good. That is good. But if that was the whole story, can you please derive the standard model now? Tell me the properties, tell me the gauge groups that you get, tell me why fundamental constants arise. Why is the muon 200 times heavier than the electron, for example? Why is the fine structure constant 1 by 137? String theory has to answer all these questions, and they don't have answers. So, the answer is no, there is a multiverse. In my universe, the fine structure constant is 1 by 137. In some other universe, it's taking a different value. We happen to be in one where it is 1. Then what am I doing? Where are those other universes? If this is what physics has been reduced to, then I don't have to do anything. I said, my universe is like this, there is another universe which is different, another which is different. So, this is my problem. So, the part of the idea was very good. Different fields and particles are different excitations of the string. Up till that, we are in agreement. But after that, what? I have to explain the world, no? I don't want to say that there are multiverses. We don't see them. We see only one universe, and I want to explain why it has these properties. So, it seems that there is some scope for making progress if you replace every space-time point right from the beginning. You don't say that one day I will remove space-time from no, you do it now. You start from there, that only then you will be able to explain what you see. Right. So, the first point we anyway talked of yesterday, second point also we have talked. Third point I just raised, why do elementary particles have such strange mass ratios. The charge ratios are very simple. Neutrino 0, down quark 1/3, up quark 2/3, electron 1. In units of electron charge, 0, 1/3, 2/3, 1. And same for all the 3 generations. Muon also 1, tau left. The electric charge ratios are very simple, but the mass ratios are not simple. The tau lepton is some 17,000 or whatever, the top quark is some 17,000 something times, some number like that. The muon is 200 times heavier, 208 times. What kind of a number is that? 208. It's not a simple fraction. Electric charge ratios are simple, mass ratios are not simple. Why do we emphasize on that? Mass has something to do with gravity. The source of gravity is energy, momentum, mass. So, if we have to understand these mass ratios as coming from some theory, that theory should have something to do with gravity. That's very obvious because mass has something. But the standard model of particle physics, strong and electroweak, is not unified with gravity. I need gravity to understand mass ratios. General relativity cannot explain mass ratios. You agree with me, no? You look at Einstein equation, there is, on the right hand side, there is T mu of ordinary matter. We don't say write down T mu of the electron or of the quark, because there is no particle physics on the right hand side of general relativity. So, general relativity is silent about mass ratios. Particle physics cannot explain mass ratios without something to do with gravity. So, we have to understand gravity better and relate it to the other forces. So, this is a problem of gravity. So, that is why I say general relativity is not the last word on gravitation. So, why does a dynamical theory such as GR have the black hole area theorem? So, what is the black hole area theorem? Whenever 2 or more black holes collide to form a new black hole, the final area is more than the sum of the initial area, more than or equal to. That is the black hole area theorem. In black hole mergers, the total area increases, never decreases. This is the direction of time. Take lots of black holes, keep merging. That time direction is one in which total area of black holes increases. But general relativity is a time reversible theory, right? It is a mechanical theory like electromagnetism. So, where has the direction of time come from? It's a classical theory. I'm not talking of black hole entropy. It's a classical theory which you can split into 2 parts. The source free part is gravitational waves. The part with sources actually is black holes. Everything will become a black hole under gravitational collapse. And then there is a direction of time. Where is that coming from? You understand what I am saying? A mechanical theory like which has Newtonian mechanics or special relativity is time reversible. It is not say, but the presence of black holes introduces a direction of time even in a classical dynamical theory like GR. So, this has probably something to do with all said and done. GR is not a dynamical theory like electrodynamics. It is an emergent phenomenon. There is an underlying theory which is time reversible and which is mechanical, but this GR may not be a mechanical theory despite appearances, and that is why even at a classical level maybe there is something underneath general relativity which is a mechanical theory. Why is the universe accelerating? Is the universe homogeneous and isotropic on large scales? There are recent observations suggesting that is probably not true. So, there will be a breakdown of Copernican principle, and once again our place will be special, not the Earth, maybe solar system or the Milky Way. Maybe we are in a special place if there is not homogeneity and isotropy on very large scales, which some people are saying now. Why does space have 3 dimensions but time only 1? This is a question of space-time, you see. It's a question for gravity. And we cannot say that I don't know what's the answer. One day we have to find the answer. maybe there are, could it be that there are 3 times and 3 spaces? Is space-time actually 6-dimensional and 2 times are hidden? Is there an absolute time apart from the coordinate time of special relativity? Last thing I talked of. And one thing I forgot to write down here, which is very important because it has to do with space-time. It is the quantum non-locality puzzle and EPR paradox. You have heard of EPR paradox? No? Yeah, I think everybody knows about the Einstein-Podolsky-Rosen spooky action at a distance. If you have 2 quantum particles with, let's say, total spin 0, an electron and a positron, they start out in opposite directions. I don't know whether its spin is up or down, but if this is measured up, this will immediately become down. And if it is found to be measured down, this will immediately become up before the measurement. So, irrespective of how far they are. So, if this is measured to be down, instantly this becomes up even before a light signal can go from here to there. So, that is the spooky action at a distance. Quantum non-locality, correlations outside the light cone. Why? Where is that coming from? It has something to do with space-time, clearly, right? And it is disagreeing with special relativity. So, that is a problem for gravitational physics. Anything to do with space-time is a problem for gravitational physics. Not just the gravitational field, the structure of the underlying space-time itself is related to issues in gravitation. So, it seems that the structure of space-time in quantum theory is not the same as in classical physics, in classical relativity. So, what is the answer? So, yeah, so these are reasons for saying that our understanding for gravitation is not complete. So, yesterday we started in the first slide with seeing sun and planets and stars, the simple picture that everything goes around the earth. We have come a long way through Ptolemy, Copernicus, Galileo, Kepler, Newton, Maxwell, Faraday, Einstein, Poincaré, and then other direction towards quantum theory, but we are not done. That does not mean this is an endless, infinite process. I mean, we are not saying that. It will be completed, but we need more time, more experiments. Or roughly from Copernicus, about 500 years have passed. I don't know how many more are needed, but we are in the process. And I like to say that we are all children of Newton. Newton was modified in 2 ways. Quantum theory is one modification, Einstein relativity is another mod, but both are in the spirit of Newton. So I was talking to one of you yesterday, and suppose I do Newtonian mechanics with matrices. You get what I am saying? Instead of with real numbers q and p, do Newtonian mechanics with matrices. That's a theory due to Stephen Adler called trace dynamics. Newtonian mechanics with matrices is more general than quantum theory. Quantum theory is a special case of doing Newtonian mechanics with matrices. So, in that sense, quantum theory is also Newtonian. It is a generalization of Newtonian physics. General relativity is another generalization of Newtonian physics, and we are trying to put them together, maybe replacing space-time with octonions and particles by matrix valued particles. Okay, so this completes yesterday's talk. We can take a 2 minutes discussion break if you want to say something.
So, DP, what kind of experiments can falsify or testify this kind of unification that you were mentioning?
1 minute here, I don't, let me say that once again, little more precise.
I understood the theoretical motivation to unify this in a geometrical way, but what kind of experiments can...
So, very good point. So, what we are right now the stage at which we are right now is what we can call post-diction. So, explain what is already known but not yet explained. Like, this, why are there 4 kinds of forces? Are there more undiscovered forces? So, predict them and then look for them. And the standard model of particle physics has more than 20 dimensionless constants whose values we don't understand, like the fine structure constant, mass ratios of particles. This is unexplained data in the same spirit as the precession of Mercury's perihelion. So, can I first make a theory which will explain this data? Right now, we don't have any string theory is not a theory like that. So, we are trying to, if I can explain the world as seen, then my predictions have some respectability. I say I can't explain, but I can predict. What's the use? When people say string theory predictions are at such high energy scales that such particle accelerators have not been built. And string theory saying it's not they are saying it's not our fault. Let CERN make a Planck accelerator, then string theory will be tested. All right, but have you explained what CERN has already measured? You have not done that. So then why should I take your predictions seriously? Yeah? So we are at this stage of first trying to explain, and then you are absolutely right. We also have to make predictions. So this is special to what the work I do with my collaborators. We predict 2 new forces. So the standard model has 3 forces. Electroweak is 2 and strong force. And on the other, separately, gravity. So we find, I am not saying this will be correct, in our work, that just as the standard model has 3 forces, the gravity sector has also 3 forces. Gravitation itself is like the weak force. This I will talk about if I get time. There is an analog of electromagnetism, which we are trying to say is MOND. You were there in the MOND discussion. The correspondence to electromagnetism is MOND, which we call dark electromagnetism. Dark electromagnetism couples to the square root of mass of particles. Electromagnetism couples to electric charge. Dark electromagnetism couples to square root of mass. Maybe if I have time I will talk. And there is a third force which we can call strong gravity, which is the analog of the strong force. So we are saying total there are 6 forces, not 4. So we should look for the gauge bosons corresponding to these new forces. For example, for dark electromagnetism, we are predicting there is a dark photon. So if you could do something like a photoelectric effect for dark photons, but these experiments are extremely difficult. So we are also in the same state a bit like string theory. Our predictions are very hard to test, otherwise they would, but at least we are not saying that it is their fault, it is CERN's fault. No. We are first still trying to explain what we see. We have not completed that task, we are trying. At the same time, so this is one prediction. The other prediction is that space-time is 6-dimensional, 3 times and 3 spaces. The other 2 times are, as you can expect, very tiny, not Planck scale tiny, but they are the scale of the weak force, 10 to the minus 26 seconds, and compact. So the current experimental sensitivity for time measurements is around 10 to the minus 19 seconds, around that range. We were saying we push that range to 10 to the minus 6, you start seeing a quantization of time. So the prediction is there are no time intervals smaller than 10 to the minus 26 seconds. Again, not immediately doable. Then the collapse of the wave function is a part of this picture, that quantum theory does not hold for macroscopic systems. if you try to make a superposition with macroscopic systems, the superposition collapses very quickly. You see what I'm saying? And quantum theory superpositions are everlasting. Yeah, but we are saying here, even before a measurement, if you try to take a heavy particle, very big molecule or a dust grain, try to put it in two places, and you make a superposition, send it through the interference double slit. Before it reaches the screen, it will collapse, and you won't see interference. If you try to make interference with very large particles, very large masses, about a billion AMU. So this is my molecules are few AMU, 700,000 AMU. But if you took a macro molecule made of a billion AMU and try to send it through a double slit experiment, you'll make a superposition, but it won't survive till you reach the screen. It will collapse to one or the other state, and you won't see interference. So if such an experiment, people are trying this. What else? A second Higgs boson is predicted, which comes with the gravity sector. The standard model Higgs boson, then there is one more Higgs boson. So predictions are there, but none of these predictions are precise and sharp numerical calculus yet. For example, Einstein predicted that the bending of light is twice the Newtonian value. So he gives you a number. Go look for this number, quantitative. So if you ask, suppose this unification theory predicts that the spectrum, say, of the hydrogen atom will be shifted by this much energy, that would be a sharp prediction. We don't have that yet. We would like to do, but we have not. Sorry. Do you get some flavor, or I can try to think of something more? Yeah.
In particle physics, there are some attempts without gravity to make a theory to predict the Yukawa planes.
Grand unification of strong and electroweak. See, their picture is grand unification happening around 10 to the 15 GeV, and unification with gravity happens at 10 to the 19 GeV. So they leave gravity out. I am not in agreement with that. Why? Because of this picture. The world at low energy looks classical, but it need not be. If you make everything quantum even at low energies, I will lose space-time. Maybe I have to replace it by octonions. Gravity will still be weak. Gravity will become strong only at 10 to the 19 GeV. But gravity is not just the gravitational force. Gravity is also space-time. The space-time manifold is fundamentally quantum in nature. So what I am saying is, please do unification at all energies. And then once you make space-time quantum, gravity will come in. It will be weak, but the underlying space-time, which is now quantum or octonionic, it places a constraint on what kind of particles you can put on that space-time, which feature is not there in quantum field theory or standard model. So they are trying to unify, they are trying to predict Yukawa couplings. I am saying you won't succeed unless you do this. So like, this Wheeler statement that space-time tells matter how to move, and matter curves space-time. So as a matter curves space-time, space-time tells matter how to move, space-time also tells matter what to be. You understand? So I try to give an analogy, like in atomic physics, before we knew atomic theory, you measure specific heats of solids. There's some arbitrary numbers. We don't understand where these numbers are coming from. That's because we did not know that matter is made up of atoms whose properties influence the properties of the solid. Then we learned to calculate specific heat from first principles. The mystery of the emerging numbers went away because we understood the microscopic structure. So, we are saying there is a microscopic structure to space-time even at low energies. They are the analogues of the atoms of space-time. If you understand that physics, you will understand Yukawa couplings and values of fundamental constants without going to high energies. Just like understanding specific heat of solids doesn't require us to go to very high, it just requires us to understand the microscopic structures. And I am saying that structure is not at the Planck scale necessarily only. It's there, but because the world is classical, I think this is a fundamental point that many people don't appreciate. So when we talk to them, they agree, but then they say how to do it. So we are right now in the how to do it phase. I don't know whether I should start the next lecture, so I will be opening the talk for discussion, but if not, then we'll at least start the next talk and stop at 11.
Can you go to the formalism part of GR, the various approaches of formalism?
Yes.
So here you were talking about the teleparallel formalism of gravity, where the effect of torsion comes into being from the antisymmetric part of the like the Leibniz-Vita connection, which is magnetry compatible. But in literature, there are concepts regarding the non-metricity also.
Yes.
So that also comes from the antisymmetric part?
No, that's even more general. See, I don't remember exactly what it is. You can have like Poincare gauge gravity, where torsion and curvature are both present. Then gravity is being described by curvature only, but torsion is a generalization of general relativity. So teleparallel gravity can be also generalized. More general teleparallel gravities will have curvature and torsion. Curvature will be general relativity, torsion will be some new interaction. I forget the definition of non-metric, but I have to look it up. Non-metricity.
Maybe the metric connection is not like the connection is not metric compatible in that case.
Yeah, that will give you torsion, but I think non-metricity is probably something even more. I'll have to look it up. I forget. I don't want to say something wrong. But torsion is very interesting. What is torsion? Why is it zero in general relativity? So, physically what the curvature does it, you take a vector around a closed loop, it doesn't come back to the starting vector because there is Riemann curvature. What torsion does is, if you try to make a parallelogram, go this way, come back parallel to the lower line, come back parallel to the side line, you won't come to the starting point. Parallel transport doesn't close loops, that is torsion. Curvature rotates a vector taken around a closed loop. The presence of torsion spoils closure of loops. So, it's definitely very, very interesting. I think we don't understand enough. So, good you brought it up. I want to say a little more. So, maybe we discuss today, not start the next lecture today. Right. There is a difference between Lorentz symmetry and Poincare symmetry. Lorentz symmetry is invariance under Lorentz transformation. Poincare symmetry includes along with that translations, right? The quantum field theories, the invariance is Poincare symmetry, not just Lorentz symmetry, because we have to bring in spin. The Lorentz symmetry is related to mass or mass energy, that's enough for GR. The additional translations part is related to spin, which is related to torsion. Why is it that quantum field theory symmetries are more general than those of general relativity? General relativity, only Lorentz symmetry. quantum field theory, Lorentz plus, namely Poincaré. So, quantum field theory is seeing mass as well as spin. General relativity is seeing only mass. If you add spin in classical GR, you bring in torsion. This looks like if you want to map GR to quantum field theory, you should have torsion. You see what I am saying? So, this mismatch is very troubling. So, we try to fantasize that the additional forces like the weak force, does that have something to do with torsion? So, yeah, this is a opening up discussion. The weak force in particular seems less like a internal symmetry of particle physics and more like a space-time symmetry of general relativity. For various reasons, the weak interaction, as you know, violates parity. Only left-handed particles take part in the weak force. But parity is not an internal symmetry, it is a symmetry of space-time. Under parity symmetry, you change the orientation of the, you see what I am saying? So, weak interaction seems to know about space-time. In that sense, it's more like a space-time symmetry. Then more. The coupling constants of the strong force and electromagnetism are both dimensionless. The coupling constant of the weak force has dimensions and same dimensions as the gravitational coupling constant. This is another similarity. Then the weak force is not renormalizable until you make it into electroweak, SU2 to SU2 cross U1. Gravity is also not renormalizable, again because both have dimensional coupling. So, like I was answering that question, gravity we are trying to write down as the weak force. SU2L, you understand? SU2 is the gauge group of the weak interaction before symmetry breaking, and we put a L for left, saying only left-handed particles take part in the weak force. So, we are trying to say that gravity is the right-handed analog of the weak force, SU2R. Last line, this is gravity can actually be derived just from a so-called chiral connection. Chiral meaning left-handed or right-handed, there is a way to define it. So, that is very, very interesting. You do not need both the left-handed and right-handed parts of the connection to derive general relativity. You need only one half of it. So, we try to write GR as a SU2R gauge theory. The weak force is a SU2L gauge theory. And where were we? Right. What was the, where did we start? Yeah. Weak force is like general relativity. That is what I am. And in a unification, it seems that the weak force also acts on a what we call a second space-time. This is just ongoing work. We have 3 space and 1 time directions. Looks like in this theory that there is a second space-time in our universe which has 3 times and 1 space. And these two overlap, 1 time and 1 space is common. The total is a 6-dimensional space-time, 3 times and 3 space. The 2 additional time directions seem to have to do with the weak force. Yeah, I still do not remember how we got here. What did you, where did we start?
We started from the formalism, like if the connection is not metric.
Yes, right. So, trying to understand, is torsion like the weak force? We have not succeeded. There is some mismatch between general relativity and quantum field theory, which is very telling. Lorentz symmetry, Poincaré symmetry, it can't be like that. You have to fill that gap. You have to bring in Poincaré symmetry into gravitation. How that will happen, I don't know. It's up for research. But it is fascinating that the weak force is like gravity. It's not like the strong force and electromagnetism entirely. Both are U1, they are Lie groups, but we want to make gravity also into a Lie group fiber bundle. That is SU2R language. and treat gravity and the weak force as the tangent space interactions, and the strong and electromagnetism and the U1 bond and strong gravity as in the fiber, and then further to unify the fiber with the base manifold using octonions. So, we are trying. I am not saying we are not close to success, but it looks very interesting. Yeah.
The tetrad formulation, in front of connection you have put a spin there.
Huh.
Connection.
Huh.
Is that there is a fermionic matter coupled?
Yes, yes. Why do we call it a spin connection? If we want to couple gravity to fermions, I must work with tetrads, not with the metric, because spinners are something deeply mysterious. If you want to talk of spinor transformations, you have to do it locally in a local Lorentz frame, which is where you need tetrads. So, the corresponding connection gets that name, spin connection. The connection, when used in the context of tetrads and fermions, is called a spin connection. That's your question, no? Yeah, that's where the name comes. But it is all said and done the same as the ordinary connection, not Levi-Civita. It will have torsion, yes. That's very interesting. You try coupling gravity to fermions, the connection will be having torsion. It's not torsion free. Already another deep point, right? Doesn't get appreciated. But what is going on here? The moment you couple gravity to fermions, you get torsion. We should think about it. Yes. Yeah, I try to emphasize there are beautiful, important problems where we should address our research. We should not leave difficult problems for others. Yeah, it's doable. It's doable. Just need to read the literature and, if I may say so, not follow trends. We need to set our own trends, for every one of us. Snail, you are not asking anything today? Ah, yes. Yeah.
What is about Ashtekar formula?
So which one?
Ashtekar formula.
Yes, yes.
What is the present status of that's
Loop quantum gravity. I am not an expert on it. I'll give you my biased subjective view. I think we cannot make a quantum theory of gravity unless we unify gravity with the other forces. That same diagram. You want to quantize gravity, to me that means removing space-time from quantum theory. What they will do, they will take the gravity action and quantize it like the other forces. You make these commutators and write the Schrodinger equation. I'm saying no, please don't do that. Tell me how to write quantum theory without using space-time labeled by real number points. Do you see? No. You don't understand. You don't get what I'm saying.
Yes, I get it.
Yeah. So, and when you do that, right, this was one criticism of loop quantum gravity. Gravity is weaker than all the other forces. When gravity becomes quantum and you couple it to fermions, other forces will come in. You couple when gravity is quantum and you couple it to matter, matter has to be described in a quantum way, like fermions. Fermions have other forces, strong and electroweak. The moment you switch on gravity, you must bring in other forces. What loop quantum gravity does, I'm not saying it's wrong, so it's my view. What loop quantum gravity does, quantizes gravity without unifying with the other forces. I'm saying it cannot be done. You put matter along with loop quantum gravity, you will get other forces. You will have to unify. So, Neither can we unify grand unification without gravity, nor can we quantize gravity without unifying it with the other forces. This is my subjective view.
But there is another approach by Padmanabhan.
Yes, yes.
Try to, I think their formalism finally lets the gravities emerge.
Yeah, there we are in agreement. There we are in agreement. Gravity is, but I used to talk to Padmanabhan. So I would then, he would say there are underlying atoms of space-time from which classical gravity emerges. Good, correct, agreed. But now, what are those atoms of space-time? I want to know, only then can I. So we are claiming, just working and testing that claim, those atoms of space-time are these octonions. Each space-time point is now to be replaced by an octonion, which is like a non-commuting, which is a non-commuting number. It has quantum properties. You see what I am saying? So we are this, in fact, we call this atoms of space-time matter. So what is an atom of space-time matter? An electron is here, you think of it as a point particle, maybe localized, and it is producing fields, electromagnetic field, weak field, gravitational field. Those fields are bosonic. The electron itself is fermionic. A particle, along with all the fields that it produces, we call it an atom of space-time matter. I don't make a distinction between the fermionic part and the bosonic part. Bosonic part is extended, but so what? The whole thing is together called an atom of space-time matter, and that has something, we think, to do with octonions and the Dirac operator. You were asking something else? Yeah? Okay.
At present, regarding the quantum gravity, there are two popular approaches, right? Like the canonical quantization and the path integral formulation. So, what is your say about these two?
Yeah, see, I'm very biased. I'm very biased, and I don't know. I don't know. You can use any bad word you want. I think it will not work unless you do this. I become very narrow-minded. Unless you unify gravity with the other forces in this sense by removing space-time from quantum theory, it will not work. That is and we are saying that we seem to be able to make progress. We also have not solved the problem, but we are trying to construct a quantum theory without classical space-time, and that seems to help the standard model of particle physics also. I'm not happy with these kind of approaches to
There are Bohemian formalism also.
Bohemian mechanics, Bohemian quantum mechanics. Okay, so now we are going in a slightly different direction. Why does the wave function collapse when you make a measurement? That is the question there. Because quantum theory is, the Schrodinger equation is linear. It is, if you make a measurement, the wave function should not collapse. The linearity should be preserved because quantum theory applies to the apparatus also, no? So then if quantum theory is not to be changed, you have the many worlds interpretation. Collapse never takes place. In my universe, the measurement should spin down. In another universe, it shows spin up. And who's there in the other universe? A copy of me. The observer also splits. Everything is splitting all the time because the Schrodinger equation is not being changed. In Bohemian mechanics, you say that there is no collapse of the wave function, there is no indeterminism. There is a randomness in the initial conditions, the so-called hidden variables, which we are not aware of. There is more information in quantum mechanics than the wave function. So different particles start with different initial random conditions, and the evolution is determined. You see what I am saying? There is no collapse, so the outcome is predicted. So Bohmian, that's Bohmian mechanics.
So in that case, there will not be any singularity.
In singularity in space-time? I don't know. Bohmian mechanics is not yet advanced enough to be applied to space-time geometry. It's mostly still non-related. So many worlds, Bohmian, and then something known as collapse theories, where you modify the Schrodinger equation for large systems. Superposition is short-lived for large systems, that's collapse theories. So when the quantum particle interacts with the measuring apparatus, it forms a superposed state, entangled state with the apparatus, but that state is very short-lived because the whole thing has become macroscopic, and it collapses randomly to one or the other. So there are three main interpretations of quantum theory: Bohmian mechanics, collapse theories, and many worlds. And experiments are not yet distinguishing between any of the three, but so that's ongoing.
So all these three have remained as theoretical artifacts only.
Yes, so I have a bias towards collapse theories because collapse theories are falsifiable. Many worlds I cannot falsify. I mean, where is my copy? I mean, I'm here. Where is my copy? I don't know. Many worlds is not falsifiable. Bohmian mechanics, most people say is not falsifiable, but some work is going on that maybe some results in Bohmian mechanics might be different from quantum theory. So yeah, right now these are, but if you look up collapse model experiments, there is quite a bit going on. But we don't have a breakthrough which will tell us whether quantum mechanics is approximate or exact. We need such a, if we find a breakthrough of breakdown of quantum mechanics, I will call that progress. What sets a time limit of 10 to the minus 27 on quantum of time? Why not any other? Very good question. The weak interaction has a length scale 10 to the minus 16 centimeters. I think it's roughly around that. We have some understanding of where does this 10 to the minus 16 centimeter comes from. It has to do with the Higgs mass, and we are trying to understand why the Higgs mass is around 100 GeV. So if I can explain why the weak interaction length scale is 10 to the minus 16 centimeters, divide that by the speed of light, 10 to the 10 centimeters. That's where the 10 to the minus 26 is coming from. It is related to the weak interaction length scale. Anything more mentioned? Oh, thank you. That was the only question in the chat? Concept, why the concept of differential geometry is why do we use differential geometry? Yeah, it seems to be the language in which gauge theories and general relativity are using the same common language. There are differences, but it's the language common to the forces of particle physics and to gravity. That is why we use that language. Curvature and connection are one forms and two forms in GR, and gauge theories also work with curvature and connection. So it's beautiful because of this unifying nature. Then concept of spinor field. Yeah, very good question. I don't think I know the answer. What is a spinor? You can mathematically define it. You can say various things, like if you rotate a vector by 2 pi in space, it comes back to the same vector. But if you rotate a spinor by 2 pi, it changes sign. So you have to rotate the spinor twice to get the same sign. Spinors is how fermions transform under Lorentz transformations. Vectors is how bosons transform under Lorentz transformations. You can think of spinor as the square root of a vector. Spinors have something very closely to do with quaternions and octonions. The square of an octonion is a spinor. I mean, these are mathematical things. I don't know what is a spinor. I mean, let me be very honest.